Hello and welcome. Today we're pulling back the curtain on the invisible architecture of our digital lives. We're going to uncover a hidden mathematical blueprint that shapes, well, pretty much everything, from your Google search results to the planes flying right over your head.
So, think about this for a second. At first glance, they have absolutely nothing in common, right? One is busy organizing a whole universe of cat videos and memes, while the other is keeping a massive 400-ton aircraft safely up in the sky. But, believe it or not, they actually share a secret architectural DNA.
And that's the secret. Deep down, underneath all the code, all the slick user interfaces, and the complex machinery, there's a blueprint. But it's not made of ink and paper. No, it's built from pure structured logic. It's kind of like the secret language that brings order to all that chaos.
All right, so that's exactly what we're going to do here. We're going to decode that blueprint. We'll start with its most basic, simple components and build our way up to the seriously complex systems that we all use every single day. So let's dive in and start at the foundation.
Now, the first thing you've got to understand is that this blueprint is completely abstract. We are not talking about geometry here. We're talking about a formal system of logic that lets us define things with absolute pinpoint precision. It lets us create a foundation so solid that we can build technology on top of it that, in theory, simply cannot fail.
Okay, so every language needs an alphabet, right? A collection of basic symbols to build words from. Well, the alphabet for our mathematical blueprint is a concept called a set. It is the absolute starting point for everything else that follows.
So what is a set? Well, it's one of the most fundamental ideas in all of math. And it's actually really simple. It's just a collection of things, or as mathematicians call them, elements. Now, these elements can be anything: numbers, people, even other sets. And what's really important is that a set is an abstract idea. The set of all the red cars in the world exists as a concept without needing some giant parking lot to gather them all together.
Now, here's a really crucial property of sets that you have to get. The order of the elements makes zero difference. The set containing the letters A and B is exactly identical to the set containing B and A. Think of it like a simple bag of things. It doesn't matter how you arrange them inside, it's still the same bag of stuff.
But let's be honest, a simple bag of things isn't going to get us very far, is it? To actually build anything with structure, like a database or a computer program, we need order. And this brings us to a new idea: the ordered pair. Now, in an ordered pair, A comma B is fundamentally different from B comma A. Just think about coordinates on a map, right? The point 2 comma 5 is definitely not the same as the point 5 comma 2. All of a sudden, order has meaning. All right, quick recap. We've got our alphabet, sets, and we've figured out a way to create order with these things called ordered pairs. So what's next? Well, now we need some grammar. We need rules that let us connect our building blocks in ways that actually mean something. And this is where relations come into play.
Formally speaking, a relation is just a set of ordered pairs. That's it. Now, I know that might sound kind of simple, but this little tool, it is unbelievably powerful. By collecting very specific ordered pairs, we can define any link or any connection between things. For instance, the relation is the capital of would include the ordered pair Paris, France. The relation is taller than could include Shaq, Kevin Hart. See? We're starting to build real meaning.
Now, some of these relations have special properties, kind of like superpowers, that make them incredible tools for logical reasoning. And one of the most important is called transitivity. It's a really simple rule of logic. If A is related to B and B is related to C, then it just follows that A has to be related to C. This property gives a relation this really nice sense of logical flow and consistency.
The is older than relation is the perfect real-world example of this. I mean, if we know for a fact that Alice is older than Bob, and we know that Bob is older than Charlie, we don't need any more information to know for sure that Alice is older than Charlie. The conclusion is just guaranteed by the logical structure of the relation itself. And this kind of predictable, reliable logic is exactly what we need to build systems we can count on.
Okay, so we've covered all these abstract ideas: sets, ordered pairs, logical rules. So what? Let's get practical and see how this blueprint actually works in the real world. We'll start by applying these ideas to the massive challenge of organizing huge amounts of data inside a database.
So first, let's talk about the problem. When data is structured really poorly, you get these sneaky, weird issues called update anomalies. This is the kind of hidden chaos that could cause your online bank balance to show the wrong number, or a social media post to just, poof, vanish.
For example, if all your employee and department info is just jumbled together, you can't add a new department until you actually hire someone for it. Or even worse, if you delete the last employee from a department, the entire department itself just disappears from the database. This is how you end up with unreliable, totally corrupted data.
So how do we prevent this mess? We need a formal rule, an unbreakable rule. And that rule is called a functional dependency. It's basically a constraint that says if you know the value of X, then the value of Y is absolutely fixed. So in the example here, an employee's social security number functionally determines their name. For any given social security number, there can only be one employee name. It's a simple rule that just enforces consistency. And the actual process of applying all these rules to clean up a database? It's called normalization. You can think of it like a purification process. Database designers find all the functional dependencies, they test their design against a series of rules called normal forms, and then they systematically break down those big, messy tables into smaller, cleaner ones that don't have those nasty update anomalies. It's literally using that logical blueprint to engineer a better, more reliable structure.
All right, let's scale this up. We've seen how this blueprint can make sure our data is consistent. But what if we need to prove that an entire piece of software, I'm talking about something like a flight control system, is absolutely 100% mathematically correct?
This, my friends, is the world of formal methods. And the goal here is nothing short of mathematical certainty. Instead of just testing software over and over and hoping you find all the bugs, you use these powerful mathematical techniques to prove that the software does exactly what the specification says it should do, and absolutely nothing else.
Now, this process really has two key parts. First up is formal specification. This is where you use that precise mathematical language we've been building up to create the perfect, totally unambiguous blueprint of what the software must do. Then you have formal verification. And this is where you use mathematical proofs to demonstrate that the actual code, the final product, perfectly matches that flawless blueprint.
And look, this is not just some academic fantasy stuck in a university classroom. Formal methods were actually used to specify a massive, major piece of commercial software from IBM called 6. This just goes to show that these techniques can be applied to huge, real-world, industrial-scale problems where reliability is absolutely everything.
So, let's step back and bring this all together. We've gone from the simplest possible idea you can imagine, a collection of objects, all the way to proving that incredibly complex software is correct. So why does this hidden blueprint matter so much? Well, because it shows us a path, a logical path from a super abstract concept like a set, to creating order with pairs, to defining meaning with relations, and finally, to building systems with so much precision and logical rigor that we can literally trust them with our data, our money, and even our lives.
You see, this mathematical blueprint isn't a limitation, it's a superpower. It's the tool that allows us humans to manage immense, mind-boggling complexity and build a digital world that is, against all odds, remarkably stable and reliable.
The principles we've talked about, clear definitions, logical consistency, rigorous thinking, they literally built our digital infrastructure. And that leaves us with one final big thought. If this blueprint of formal, structured thought can help us build better technology, where else? Where else in our lives, in our societies, and in our institutions could it help us build a better world?